آره الان ریکه دیگه.
خب اوکی اینو کنسل کن. روز میشیم سسترا میکنیم سوت میزنیم. نون پنیر برای أعوذ بالله من الشيطان الرجيم
کنون خردمند وصف خرد بدین جایگه گفتن اندر خورد. خرد بهتر از هر چه ایزد بدار، ستایش خرد را به از راه دارد. با نام یاد خدا، سومین دوره از سری سمینارهای زمستانی مباحث پیشرفته در علوم و مهندسی کامپیوتر را آغاز می‌کنیم. بنده به نمایندگی از کمیته برگزاری WSS 2017 خوش آمد عرض می‌کنم خدمت شما حضاران، خدمت شما حضار عزیز، اساتید عزیز دانشکده و صمیمانه قدردان حضور شما هستیم. عذرخواهی ما رو بپذیرید برای تأخیر پیش آمده این سری عدم هماهنگی بود با سالن. سمینار زمستانه به همت قریب به 50 نفر از دانشجوی دانشکده به همت 2-3 ماهه تلاش 2-3 ماهه بچه‌ها برگزار شده. از سخنرانانمون اگه بخوام بگم 11 تا از سخنرانان ما از اساتید دانشگاه‌های خارج از کشور هستند. 7 نفر از اونها پست‌داک هستند و بقیه دانشجوهای دکترا از 24 دانشگاه و مرکز تحقیقاتی غربی مثل استنفورد، ETH، پرینستون و مرکز تحقیقاتی مثل MIT، IBM، باستون لب، گوگل ریسرچ، گوگل دیپ مایند و از حوزه‌های متنوعی از بیوانفورماتیک، اینفورمیشن تئوری گرفته تا اپتیمایزیشن الگوریتم و ماشین لرنینگ. در مورد شرکت کننده ها، حدود نیمی از شرکت کننده ها دانشجوی کارشناسی هستند. حدوداً 35% شرکت کننده ها دانشجوی ارشد و بقیه هم دانشجوی دکترا یا دکترا و محقق هستند. اینجا میخوام تشکر ویژه‌ای بکنم از اسپانسرهامون، شرکت سهام پرداز و شرکت پوشه، و قدردانی بکنم از شبکه انتشار دانش نودی و مؤسسه ایران نالج که به ما در تامین هزینه سفر مهمانانمون کمک کردن. و چند تا نکته رو هم باید یادآور شم همینجا. ما فرض رو بر این گرفتیم که شما کانال WSS رو دنبال می‌کنید، آدرسش رو باید نمایش بدیم و بات WSS، راهنمایی مکانیابی، راهنمایی تالارها، راهنمایی سخنرانی‌ها تو باتمون هست و کتابچه‌ای هم توی تک در اختیارتون قرار گرفته که موضوع هر سخنرانی، ابسترکت سخنرانی و برنامه زمانبندی‌ها اونجا اشاره شده بهش. و نکته آخر همین که در کتابچه‌ای که در تکی که خدمتتون داده شده نوشته شده نحوه دسترسیتون به اینترنت، شریف آیدی رو چطوری برقرار کنید و چطوری میتونید از اون استفاده کنید. انشالله استفاده میکنید. من میخوام که از آقای مطیعی دعوت کنم. آقای مطیعی فارغ التحصیل دانشکده خودمون هستن و الان دانشجوی دکترا در دانشگاه یونیورسیتی آف کالیفرنیا سان دیگو هستند و دبیر علمی WSS. ازشون دعوت میکنم تشریف بیارن.
سلام و خیر مقدم عرض می‌کنم خدمت همه حضار گرامی، اساتید گرام و محققان و همین پژوهشگرانی که در خدمتشون هستیم. همونطور که خیلی از عزیزان با خبر هستن، WSS اول بار 2 سال پیش به همت سرکار خانم دکتر مهابادی که اون موقع دانشجوی دانشگاه امارتی بودن و آقای دکتر صادقی، خانم خانیپور و خانم شامخی و با همکاری دانشگاه دکتر بورسی و صد البته انجمن علمی دانشکده کامپیوتر به عنوان مجری اصلی آغاز به کار کرد. همون دوره آقای دکتر قندهاریزاده رو به عنوان کینوت اسپیکرمون داشتیم. امسال هم ایشون یک افتخار ما دادن که در خدمتشون باشیم. هدف سمینار استفاده از فرصت تعطیلات بازار کریسمس هست و گردهمایی محققان و پژوهشگران داخلی و خارجی حوزه علوم و مهندسی کامپیوتر. خیلی خوشحالیم که تونستیم توی این 3 سال برنامه رو پایدار نگه داریم. از تمام اساتید دانشگاه و تمام دانشجویانی که ما یاری کردن توی این 3 سال، واقعا بدون کمک نفرات اصلا امکان پذیر نبود رسیدن به همچین برنامه‌ای برای امسال. و تشکر می‌کنم از انجمن علمی و تیم برگزاری این رویداد. امسال من یه مختصری از گذشته بهمون رو خیلی سریع خدمتتون ارائه میدم. تعداد سخنرانان سال اول 24 نفر بود، پارسال 30 نفر بود، امسال 28 نفر سخنران و 3 نفر از اساتید هستن که برای پنل در خدمتشون هستیم. تعداد دانشگاه سال اول 16 دانشگاه سخنران داشتیم، سال دوم از 18 دانشگاه، امسال از 27 دانشگاه و سال قبل اصلا ورکشاپ نداشتیم. امسال به پیشنهاد و با تمام زحمات خود انجمن علمی و تیم برگزار کننده رویداد 8 تا ورکشاپ داشتیم دیروز و پریروز که احتمالاً خیلی از عزیزان شرکت کردن و بسیار تشکر می‌کنم از آقای عبادیان به عنوان مسئول برگزاری از سمت انجمن و تمام بیش از 50 نفر از عزیزانی که شبانه روز کار کردن. یعنی خیلی از بچه‌ها دیشب نخوابیدن و من می‌دیدم به شدت زحمت کشیدن و امسال هم امیدوارم که نتیجه‌شو ببینیم و سطح رضایت عزیزان و مردمی به اندازه قابل قبولی باشه. در نهایت دعوت کنم از آقای دکتر موفق استاد تمام دانشکده کامپیوتر که ما افتخار دادن که یه چندی در خدمتشون باشیم و آقای دکتر موفق دارم شما.
یکی از همکارانم در حضورتون هستم به دستان شورای دانشکده یک نیم ساعتی دیگه برگزار میشه و اساتید مورد درگیر شورا هستن. دقیقاتی پیش خدمت آقای دکتر من صحبتان بسیار تعریف میکردن از برگزاری تا اینجا و واقعا دست برگزار کنندگان در نکنه فوق‌العاده عالی است. امیدواریم خیلی بهتر از بسیار سال پیش و سال پیشتر. من نمیخوام خیلی وقت رو بگیرم، فقط یک صحبت کوتاهی در مورد زمینه مهندسی و علوم کامپیوتر در جهان، در کشور و اهمیت این سمیناری که شما دارید در اون کانتکست خدمتتون خواهم داشت. اولا واقعا از نظر به اصطلاح تاریخی بحث الگوریتم و بحث کامپیوتیشن یا محاسبات سابقه دیرینه‌ای در این به اصطلاح حوزه تمدنی که ما هستیم داره، خیلی ریشه دار هست. یعنی من نگاه می‌کردم در اینترنت، جالب 2300 تا 2700 سال قبل از میلاد سومری‌ها که در همین حوزه تمدنی ما زندگی می‌کردن اولین بار چرتکر رو برای محاسبات ارائه کردن و استفاده می‌کردن. جالب می‌بینید 2000 سال پیش از میلاد خیلی گذشته خیلی است برای اولین بار. و بعد مبنایی که استفاده می‌کردن مبنای 60 و از همون سومریاست که ما 60 دقیقه 60 ثانیه اینها رو داریم. در واقع محاسبات، وسیله محاسبات چون و جالبه بدونید در 600 قبل از میلاد ایرانی ها در مثلا امپراتوری هخامنشی چرتکه خیلی زیاد استفاده میشد. منتها دیگه خب این مبنا شاید دیگه تغییر کرد و به گونه این اصطلاح چیز بود، رایج بود در دوره اشکانیان، در دوره ساسانیان و به همین صورت و واقعا از طریق ایرانی ها بود که به هندوستان، به چین و به امپراتوری روم هم این به اصطلاح چرتکه رفت و البته یونان 400-500 سال قبل از میلاد چرتکه جوابی رو اونجا دیدن. اونجا اینا همش معروفه و من فقط می‌خواستم خدمتتون عرض کنم این حوزه تمدنی که ما الان درش هستیم اصلا تا اونجایی که الگوریتم و محاسبات و اینا برمیگرده تو دنیا سابقه بسیار بسیار ریشه‌داری رو داره. و جالبه بدونید بعد از اسلام، حالا قبل از اسلام ما پدر در واقع الگوریتم یکی از اونها اوگلیدوس بوده که این بزرگترین محصولای مشترک 300 سال به اصطلاح قبل از میلاد و اون الگوریتمی که اوگلیدوس داره و هنوز هم استفاده میشه. ولی بعدش واقعا یه فرق خیلی کلیدی ابو موسی محمد بن جعفر الخوارزمی است که اصلا انقلابی رو برپا کرد. اعداد عربی، هندی که مصطلح هست در دنیا در واقع حدود 1200 سال پیش اون رو مطرح کرد و همین الگوریتم‌های ضرب و جمع و اینایی که ما بسیار باش آشنا هستیم واقعا برای اولین بار ایده‌های نو بود، فوق‌العاده مهم بود. 400 سال طول کشید که در حدود 800 سال پیش فیبوناچی، ریاضیدان خیلی معروف ایتالیایی، در یک کتابی که در واقع محاسبات به نام لیب دو اباچی به لاتین به معنی که کتاب محاسبات، اون رو به لاتین بعد 400 سال معرفی کرد. این به اصطلاح دستاورد خوارزمی که در تمدن اسلامی استفاده میشد، یعنی در بازرگانی، در برنامه امور مالی حجت استفاده میشد. منتها بعد 400 سال به اروپایی‌ها اینو معرفی کرد و جالبه از اون موقع تا 200-300 سال اروپایی‌ها قبلش اعداد رومی استفاده می‌کردن که خب طبعا صفر نداشت، به علاوه همین چرتکه. و بعد 200-300 سال رقابت بود بین الگوریتمیست ها، یعنی اونایی که از ایده خوارزمی برای محاسبات مالی استفاده می‌کردن بدون چرتکه، و چرتکه‌ای‌ها که در واقع اونایی که در خصوص روم و اون رول وسطا در اروپا از همون سیستم سنتی قدیمیشون استفاده می‌کردن. تا این میرسه به حدود 1500 سال پیش، 600 سال پیش دیگه الگوریتمیست ها پیروز میشن. و جالب خود الگوریتم هم همونطور که می‌دونید فکر کنم اولین بار لیبنیتز رو مطرح کرده بود به عنوان همین چیزی که ما می‌فهمیم لاتینایز در واقع اسم خود خوارزمی است. و حدود 400-500 سال دیگه در غرب دیگه الگوریتم و اعداد در واقع دهدهی اعشاری که ما الان استفاده می‌کنیم رایج شد، دیگه فراگیر شد. چرتکه مقدار دیگه فراموش شد. یعنی چرتکه‌ای‌ها تو اروپا شکست خوردن، الگوریتمیست دیگه فراگیر شد. خب این در مورد سابقه واقعا تمدنی ما در حوزه محاسبات و در حوزه الگوریتم که ریشه واقعا بنیان رشته علوم و مهندسی کامپیوتر هست. رشته علوم و مهندسی کامپیوتر رشته جدیدی هست. همونطور که می‌دونید بحث‌های تئوریش از دهه به طور جد از دهه به اصطلاح 30 میلادی با گودل، تورینگ، چرچ و اینها در واقع پایه گرفت. و بعد اولین کامپیوتر در 1940 خورده کندومن درش خیلی در بود و به اصطلاح ساخته شد به طور جدی. در نتیجه کامپیوتر یه حوزه جدیدی در دنیا. اما به ایران که ما میرسیم ما حتی قبل از انقلاب زمینه‌های کامپیوتر رو داشتیم و من در همین دانشگاه شریف، دانشگاه تهران هم همینطور زمینه‌های مربوط به کامپیوتر یا در دل دانشکده برق مطرح می‌شد یا در دل دانشکده ریاضی. این آمد تا بعد از انقلاب در سال 1364 اولین دانشکده مهندسی حالا علوم کامپیوتر، مهندسی کامپیوتر تأسیس شد در همین دانشگاه صنعتی شهر. و در واقع رشته کامپیوتر الان نگاه می‌کنیم یه هویت جدی گرفت. قدمتش حدود 34 سال هست، نسبتاً جوان. و این انقدر الان اوضاع به هر حال رو به پیش بوده در همین حوزه مهندسی علوم کامپیوتر در کشور. البته شما خودتون بهتر می‌دونید الان 30-40 سال پیش بزرگترین شرکت‌های مثلا دنیا جی ام و نمیدونم فورد و اینا بودن. الان دیگه گوگل و به اصطلاح فیسبوک و اینا هستن. حوزه کامپیوتر در کشور ما هم فوق‌العاده مهم شده. من همین الان فقط می‌خوام خدمت عرض کنم جای بسی افتخار هست که کنکور سراسری که ما داریم تعداد زیادی از دوستان در حوزه علوم ریاضی اینا شرکت می‌کنن، شاید چندین صد هزار، رقابت بسیار تنگاتنگیست. بالاترین رتبه‌ها الان 1-2-3 ساله نه تنها در دانشگاه شریف بلکه در دانشگاه‌های دیگه کشور ما هم رشته انتخابیشون رشته کامپیوتر هست. یه برق نیست، کامپیوتری. و خب حوزه‌های مربوط به کامپیوتر بیگ دیتا رو میگم تمام اینقدر مهمه که همونطور که خدمتتون عرض کردم تولید ثروتی که الان در جهان میشه عمدتاً اینا هستن که تولید ثروت کلان دارن میکنن. بزرگترین شرکت‌ها الان شرکت‌های حوزه فناوری اطلاعات و به هر حال کامپیوتر ساینس و کامپیوتر انجینیرینگ هستن. ببینید این همت که دوستان ما، دانشجویان ما انجام دادن در سطح دانشگاه بی‌نظیر. من خودم مسئول بین‌الملل دانشگاه بودم، اینو به جد میگم. رشته‌های متعددی ما داریم، فقط بچه‌های کامپیوتر البته ازشون انتظار میره اینا دیگه الان طلایه دارن. خب فوق‌العاده عالی است. فقط دقت بکنید ما ایرانیایی که در خارج از کشور داریم در کشورهای پیشرفته هم از شرق هم از غرب، امریکا، کانادا، استرالیا، حتی چین، روسیه و از حضور شما در سراسری که هندوستان، در سراسر دنیا الان بچه‌های ایرانی دارن تحصیل میکنن، تحصیل علم. و تو حوزه کامپیوتر که این ثروتزاست، این پتانسیل عظیمی که ما داریم، این asset بزرگی که ما داریم، واقعا باید ازش استفاده بکنیم دوستان. یعنی این کاری که بچه‌های ما در واقع داوطلبانه دارن میکنن خیلی عالیه. انشاءالله را با داشتیم صحبت میکردیم، این یه مقدار پتانسیل بسیار بالایی بوده، چون ارتباط سینرژیک بین محققین ایرانی که در خارج از کشور هستن و علاقمند هم هستن به این آموزات بسیار زیاد و اینایی که اینجا هستن مثل ما و این دانشجویان ما. خب این ارتباط اگر تقویت بشه بسیار به نفع همه هست، تولید ثروت میکنه در کشور. اینو باید واقعا خیلی جدی بگیریم و منم معتقد نیستم که ما اینو ببریم در حوزه‌های دولتی و اینا. باید همینطوری باشه، غیر دولتی، داوطلبانه. دانشکده ما به هر حال مفتخره، اساتید ما آقای دکتر صامتی ریاست محترم دانشکده کار داشتن برای من دست شورا به من می‌فرمودن از بچه‌ها تشکر کن. یعنی ما می‌دونیم این یک فرصت بسیار طلایی است، قطعاً کمکتون خواهیم کرد. انشاءالله امسال بسیار بهتر از سال پیش، سال آینده بسیار بهتر از سال بعد. به هر حال خیلی مفتخریم که در دانشگاه ما شما حضور دارید، چون من می‌دونم دوستان از سراسر کشور اومدید، دانشگاه‌های دیگه، به خصوص و به ویژه واقعاً ایرانیان بسیار عزیز ما که از خارج از کشور لطف کردن و افتخار دادن اینجا تشریف دارن. ما بسیار از شما متشکریم. من فکر میکنم الان اگر یه مقدارم تعطیلی هست میبخشید، احتمالا آقای دکتر قندهاریزاده رو من یه معرفی اجمالی داشته باشم از اساتید برجسته دانشگاه کالیفرنیا جنوبی. پس آقای دکتر تحصیلاتشون همش در یک از دانشگاه فوق‌العاده زیبای امریکا، ویسکانسین مدیسن انجام شده، لیسانس، فوق لیسانس، دکترا. یکی از جای رویایی است واقعا. دانشگاه بسیار بسیار عالی. البته USC هم بسیار بسیار عالی است. آقای دکتر فکر می‌کنم بیش از 2-3 دهه دیگه 2 دهه است در اونجا عضو هیئت علمی هستن. تحقیقاتشون فوق‌العاده الان در که واقعا ثروت‌زاست. من دارم خدمتتون عرض می‌کردم بیگ دیتا و حالا به طور اجمال the design and implementation of a scalable highly available، حالا پرانتز always on، یعنی با نزدیک به 100% دیگه، and elastic data driven infrastructure. ببین این یک حوزه‌ای است که فوق‌العاده مهمه، همین که خدای دکتر هم اشاره فرمودن و از بحث‌های کلیدی این حوزه هست. و بعد his research contribution has been recognized by numerous awards, including the ACM Software System Award and NSF Young Investigators Awards. بسیار prestigious هست این جوایزی که آقای دکتر کسب کردن. در حال حاضر we have organized the Foundation and Applications of Blockchain 2018 and the General Chair of Very Large Database 2019. من خواهش می‌کنم آقای دکتر تاکشون در مورد Cache Augmented Data Store Solution and Opportunities. آقای دکتر قندهاریزاده افتخار بدید و در خدمتتون.
صبح خیر. میخواستم اول از همه از دانشجوها تشکر بکنم که این برنامه رو هر سال گذاشتن ظرف 3 سال اخیر. دوم از همه میخواستم از آقای دکتر تشکر کنم برای اینتروداکشن خیلی قشنگی شد. The rest of the talk is going to be in English, so the vocabulary is in English, therefore I must speak in English. So the lecture today is about cache augmented data stores, solutions and opportunities. I'm a faculty member at the University of Southern California, and I direct the USC Database Laboratory. Here's the outline of the talk. I start with brief words of motivation to motivate the cache augmented data stores. I'll tell you about 3 challenges and solutions that are out there, and I'll tell you about an opportunity that is on the horizon. I will conclude with a problem. I was asked to introduce you to a problem should you want to solve it. And that will be at the very end of the talk, where I will challenge you with a research question that is out there. So the focus of cache augmented data stores is on simple operations. These are operations that read and write a small amount of data. So every time you use Facebook to view someone's profile, you're performing a simple operation. When you use Wikipedia to look up a wiki page, you're performing a simple operation. When you go to Bank Sadarat and you withdraw money, you are performing a simple operation. When you go to Bank Melli and you look up the balance of your account, you are performing a simple operation. The challenge is that there is a high volume of requests out there. There are many people that are performing that same operation concurrently, simultaneously. And it's very important for the system to process the request very, very quickly. When you look at the social networking sites out there, such as Facebook, they claim to process in excess of 100 million queries every minute. They have in excess of 1 billion members competing with China and India as far as their membership is concerned. And on a daily basis, they have 700 million unique visitors. That's twice the population of the United States. I believe that's approximately 12 times the population of Iran. Imagine 12 times the population of Iran visits Facebook on a daily basis. And they are being processed very quickly, within a fraction of a second. And there are many more examples out there from Google and from Twitter, from LinkedIn and others. I've just shown you a sample of a few of those sites that are processing simple operations at a very high velocity out there. So the question is, how do they do so? And the way they do it is that they look up query results instead of processing queries. So this is ideal for applications with workloads that exhibit a high read-to-write ratio. Think of it this way: when you use Telegram and you view someone's profile, it rarely changes. You may view that profile frequently, and instead of the system computing that profile every time, it can compute that profile once, store it on the side, and then the next time around that you access it, it just looks it up and retrieves it instead of doing any processing. So in these systems, they're using key value stores. These are main memory distributed key value stores as the cache manager. And in its simplest form, you can think of the caching as the query string being the key, where the query is the SQL syntax, for example, and the value is the result set of that query that has been serialized and stored in the cache manager. And we are talking about trillions of key value pairs. A very large number of these key value pairs are being stored in the caches out there. The way these cache augmented data stores are organized is as follows. You essentially have a relational database management system on the side. Think of it as MySQL or Oracle. And you also have a cache server, an in-memory cache server, such as Memcache. And then at the top level, you have the application. Think of the application as Telegram or Facebook. Every time a request is issued to that application, the first thing it does is that it looks up the cache for the result. That's the first step. If the value is found, then it jumps to the very end by using that value to produce the results. That's step 6. On the other hand, if the cache reports that the result doesn't exist in the cache, then the application in step 3 issues the necessary SQL queries to the relational database management system and uses the query results to construct a value that corresponds to that key. And in step 5, stores the key value pair in the cache manager for future reference. So essentially every time there is a cache miss, it starts to populate the cache for future references to come. Should there be an update where the database management system is updated by an insert, delete, or an update command, essentially the programmer, the software developer, is responsible for writing the code to invalidate the key value pair. By deleting the key value pair from the cache server, a subsequent reference for that key observes a cache miss. And that cache miss causes the system to query the database management system to access the latest results, to compute the latest key value pair to store in the cache manager. This invalidation is a very expensive operation, so I'm going to use it because it's simple to explain and simple to reason about. But the truth is that the real systems out there, like Facebook, they really use the write true or the write back policy, which is more complex. The idea is that instead of deleting the key value pair, the application updates the value of the key that's stored in the cache. The software becomes far more complex, but the system becomes far more efficient and it consumes less power in order to do the processing that is demanded from it. So for the rest of this lecture, assume, invalidate, but recognize that there are other policies that are being used out there. There are different ways of architecting these systems. There is the client-server architecture, where the application is using the data store client to access the data store server, and that data store client is concurrently able to access the caching layer. You should think of the caching layer as consisting of hundreds, if not thousands, of servers. So think of a data center setting, where I have thousands of servers that are just for the caching layer, and hundreds of servers just for the data store layer that is out there. Using this architecture, a system that could do, say, a few hundred requests per second. So on this slide, I'm showing you the performance of a system for a benchmark. And on the y-axis, I'm showing you the different read-write mixes that are out there. An industrial strength relational database management system that could do a few hundred actions per second can suddenly do close to 12,000 actions per second. If you increase the ratio of the write actions, obviously the cache becomes less relevant, but still it's providing in excess of 10,000 actions per second as far as the processing is concerned. The performance numbers that you're seeing here is attributed to one of the students from Sharif University. So Sumita Barahman was a PhD student at USC, and she's the inventor of this BG benchmark, which is a macro benchmark for interactive social networking actions. BG quantifies the social action rating of a data store. So in her dissertation, she articulates that for a given workload, the maximum number of simultaneous actions performed by a data store while satisfying a pre-specified service level agreement is the source of that system. Her work was recognized by Google in the form of a PhD fellowship, and currently she is at Microsoft. So using the BG benchmark, we are able to show that with a service level agreement that requires 95% of actions to be faster than 100 milliseconds, using the cache augmented data store, we can enhance the performance of the system 30 times higher. An alternative to the client-server architecture is the shared address space architecture. The idea is to put the cache within that data store client. Don't separate it, push it into the data store client so that it's integrated with the application. The reason why this is useful is because it avoids the overhead of serializing the payload and transmitting it across the network. By avoiding this overhead, suddenly the performance gets boosted 10 times higher. Now we're talking about 140,000 actions per second, just by changing the architecture. Now, suddenly it can do 400-fold enhancement just by adding the caching layer to the system. It just gets a kick and can process far more requests than it could do before. You may ask why, and the reason is simple. Query processing requires CPU processing, and the CPU overhead of query processing is well documented out there. The studies that you see below report that the overhead of query processing is 85% of the CPU cycles that are out there. And by just avoiding that overhead, you can get the performance boost by looking up the results that are out there. So let me tell you about a few, based on this architecture and based on the workload of simple operations, let me tell you about a few challenges and the solutions that are out there that are very recent. One of the challenges is strong consistency in these systems. So when I talk about strong consistency, I'm talking about ACID properties. ACID stands for, ACID is in the sense of computer science, not chemistry. Stands for atomicity, consistency, isolation, and durability, properties of transactions. And the consequences of violating strong consistency is that you may look up Facebook and you just friended someone, but it's showing the old number of friends as far as how many friends you have. Or it may reverse ordering of comments and the responses that are out there, where the sequence of comments doesn't make sense. They've been shuffled around. Or a shopping cart that has extra items or misses items that you did put in your shopping cart. So the key insight here is that by taking a relational database management system and augmenting it with a cache, it's no longer aware of that cache, and it's possible for the application to insert stale data in the cache due to undesirable race conditions, and also a setting of the database management system that's referred to as snapshot isolation. The numbers that I showed you for the industrial strength database management system is based on snapshot isolation. If you take away snapshot isolation from the DBMS, the performance goes down dramatically. So, but it does result in stale data with the cache augmented data store. Let me show you with an example what happens when we have concurrent actions coming into the system. So consider the following scenario. Imagine I have Alice who logs in to, say, Telegram or Facebook. At the same time, I have the administrator who has seen Alice violate the rules of the site. So the administrator is trying to delete Alice's member profile from the underlying system. So these are two concurrent transactions that are being issued. With the first transaction, the site administrator's request is pretty simple. He or she wants to delete Alice's record from the database management system and delete the corresponding key value pair from the cache server. So as a function of time, it's two distinct operations. Delete her from the DBMS and delete her corresponding key value pair from the cache. As far as Alice is concerned and her transaction, Alice is looking up her profile and her request observes a cache miss. So when it does a get key, it gets a miss, so it issues the queries to the relational database management system to compute the key value pair and inserts that key value pair in the cache. So those are the three distinct steps that are happening. There are two possible serial schedules. So for those of you who have taken an introductory course to database management systems, they talk about serial schedules. So even though these transactions are executing concurrently, the two possible desirable schedules are that either Alice's actions are performed first, followed by the administrator, or the administrator is performed first, followed by Alice. In other words, with the first one, you will have, for example, Alice's actions, which is doing the get and it populates the cache, and then the administrator deletes. Notice that with the first schedule, at the very end of time, Alice is gone from both the database management system and the cache. With the second possible serial schedule, we have the administrator go first. So the administrator deletes Alice from both the DBMS and the key value store, and then Alice comes along, gets a mess, tries to compute computes nothing because there is no record and inserts nothing into the cache manager. Observe that with both of these serial schedules, Alice is gone for good from both the database management system and the cache manager. A subsequent lookup for Alice returns Alice not found. The cache and database are consistent with one another. And now I'm going to show you a race condition that makes Alice come alive, even though she was supposed to be deleted. And before I show it to you, I want to tell you that this has nothing to do with the cat here that is out there. It has nothing to do with the distributed systems and the network partitions that may exist. It's actually a healthy system that suffers this desirable race condition. Because the actions are interleaved, you may have a scenario where Alice's actions are sandwiching the administrator's actions. So Alice does a get, observes a miss, queries the DBMS. At the same time, the administrator deletes her from the DBMS and the cache. But then Alice's transaction continues and inserts her into the cache. Now you have a scenario where Alice is in the cache with no corresponding record in the relational database management system. If the administrator looks up Alice, Alice exists. If Alice tries to log into the system, she can log in. She has no problem. So this is an example of an undesirable race condition that causes the cache and the database management system to fall out of sync with one another. And it's producing stale data. It's producing data that should not be there. And the scenario that I hinted at is the snapshot isolation, which can cause stale data to be inserted into the cache. The concept of snapshot isolation is very simple. When you have a read-write transaction that are executing concurrently, the database management system may use different snapshots of the system to process the read request. So the write is producing a new snapshot of the database, while the read is using the old snapshot in order to compute the results. This is acceptable because it results in serial schedules. You can say the read happened before the write, based on the concurrency that's happening. So once again, we can have the scenario where the query is competing inside of the DBMS, and it's the case that the deletion is happening concurrently, that's creating the new version, but the query is based on the previous version. And once again, it inserts Alice in the database management system, even though as far as the administrator is concerned, she should have been deleted. So once again, we have a scenario where the cache is no longer in sync with the database management system. So there are several possible approaches to address this challenge. One of them is to modify the key value store only. Alternatively, you can modify the relational database management system. Yet another possibility is to modify both the DBMS and the key value store. And then, of course, you can consider one of the first three in combination with changing the application. Unfortunately, many are using approach 4, and it's a very, very expensive approach that is out there. The approach that I'm going to describe to you is going to modify the key value store only. And the reason why we strive to modify the key value store only is because it's very simple. When you compare the key value store with the relational database management system, it's relatively younger. Relational database management systems are now 25 years old and they are very complex. Key value stores are approximately 10 years old and they are far simpler. And I'm going to introduce the IQ framework that extends the key value store in order to address the challenge that I just described. So it's going to make changes to the client component of the key value store, the volume client, and the key value store itself. For example, the memcache itself. The advantage of this approach is that it will function with all database management systems that are out there. It will work with Oracle, Microsoft, SQL Server, MySQL, and the others that are out there. KVS components are far simpler than the relational database management system, and it provides for transparent caching that I will describe to you towards the end of the talk. So with the IQ framework, there are two pieces. there is the inhibit list and there is the quarantine list. And it's implemented both by the KVS client and the server. Instead of telling you the details, let me show you how it works. So with the inhibit list, it's granted to a cache list. So when Alice issues her get command and it returns a miss, the cache server grants an IList to that request. In order for the insert operation to succeed, it must provide that list. It's like a token. It's like your passcode for Banque Melli that you insert. Essentially, the system is generating the code every time there is a cache list. And the caller must provide that token in order to be able to insert. So it will insert if the IList matches. Otherwise, it will reject the insert and release the IList altogether. So the quarantine list invalidates the IList for the reference key. And by doing so, it prevents the insert from inserting stale data into the cache. So in this example, as you can see, Alice's request is issued for the get, observes a miss, the IList is granted, she queries the DBMS, and then the administrator comes along, deletes the DBMS row, and issues a queue list. Currently, it's the same key value pair. Once that request is issued, the IList is revoked. Now, when the insert comes along by Alice, because the list no longer matches, that insert is rejected. And the cache remains empty. So there is no IList at that point, it ignores the insert, and by doing so, the cache and the database remain consistent with one another. The queue list is released by the KVS delete operation. So once the queue list is granted, at the very end, when the delete for the key value pair is issued, at that time the queue list is released, and then the subsequent inserts will start to populate the cache manager. The same applies with the snapshot isolation. So the queue list forces an IList to back off and try again. It essentially shifts the get request from the cache to happen at some time later. That's the basic idea here. So consider the scenario where the administrator's delete request is issued once again and the queue list is requested. Once the queue list is granted, that get that observes a miss is pushed back in time. So when the get request is issued, it encounters the queue list on that same key value pair, and now it's time shifted. It's pushed back. It must wait until that queue list is released before it can obtain the IList in order to proceed to populate the cache. So by doing so, it forces the querying of the DBMS to happen for the latest version of the data inside of the database management system. And it ensures that the cache and the database remain in sync with one another. So I'm going through a lot of details very quickly with examples, but I want you to know that all these techniques also work for the write-through policies. So far this has been in the context of invalidations where the key value pair is deleted. But if the application is actually updating the key value pairs, it's the case that the truth table changes, but it can handle these more complex scenarios as well. The CPU overhead, if you're wondering about the performance penalty of this technique, is minimal. So we've used the BG benchmark to look at the store of the system with and without these IQ leases. And it's the case that the highest overhead is imposed when the CPU of the cache server is 100% utilized. And it's really the case that the performance penalty is marginal. It's not that much in order to implement this solution. So as far as this challenge is concerned, the proposed solution based on the IQ framework provides strong consistency. It operates in 3 modes: invalidate, refresh, incremental update. It has a very simple programming paradigm. The overhead is in the form of CPU cycles and it's negligible. And it's available for you to download. So if you're using Memcache to build systems today, you can actually download a version of Memcache that we've posted on DB Lab to play around with these lists. Let me change track and tell you about a second challenge that is out there based on these cache augmented data stores. And that deals with memory management. So as most of you know, today we use a hierarchy of memory devices. We use DRAM or RAM, it's also referred to as memory, and magnetic disk as a persistent form of storage for the volatile DRAM. The data is stored on the disk, and it's many times larger than the size of memory. So the data on the disk may be in the order of terabytes, whereas the size of the memory may be in the order of gigabytes, tens if not hundreds of gigabytes. It's also the case that the memory is much faster than the disk. So you really want the memory to process most of the requests. So just to give you a perspective, the access time to memory is in the order of nanoseconds, whereas the access time to the disk is in the order of milliseconds. So if a nanosecond is 1 second, 10 milliseconds is 2 weeks. If a nanosecond is me reaching to pick an object from here, 10 milliseconds is my extending my hand all the way to Los Angeles, California to pick something. So huge difference between the speed of memory versus disk. You don't want me to stretch my hand all the way out there. It's going to be very time consuming. So you want memory to process as much of the requests as possible. This raises two questions. First of all, how do you manage the memory space? And what data items should occupy memory? When you look at the operating system literature, it's really the case that they take the data and the memory and they partition it into fixed size chunks, say 4 kilobyte. And then they have the data chunks compete for the memory chunks. The question is, what data items should occupy memory? And it's really the case that Peter Denning back in 1968 introduced the least recently used algorithm. So the idea is that when a new page is needed, the buffer pool manager drops the page from the buffer that has not been accessed for the longest time. That's the LRU algorithm. Here's the pseudocode for LRU algorithm. Essentially, when a page reference is made, if the page is sitting in the buffer pool, then its last timestamp is updated to be the current timestamp. Otherwise, it sets the min to be the current time plus 1, and it scans all the pages in the buffer pool, all the frames, and finds the page which has been least recently referenced. That's the victim page. If the victim is dirty, then it writes that disk page to the disk drive. And then it fetches the reference page, that's the input, into the buffer frame that was held by the victim, and sets the last timestamp of that frame to be the current time. Now, most of you know that no computer ever implements this algorithm because its complexity is too high. If I have a buffer pool with 1 million frames, its complexity for selecting a victim, the worst case scenario, is order 1 million pages. So, an efficient implementation of this algorithm is based on a queue. The way they implement it in operating systems is that they maintain a queue. Every time a page is referenced, they push it to the tail of the queue, and the victim is always at the top of the queue. So order 1, in one operation they can identify the victim in order to implement that complex algorithm. LRU has its own limitations. It decides what page to drop from buffer based on too little information. It's based on the last reference, and that's just too little of information. When you consider a cache augmented architecture, a key value pair has a size and a cost. And the key question is, how will you consider the size and the cost? There are different definitions for a cost. Let me give you an example. Facebook uses machine learning algorithms to compute certain key value pairs that decide what data it should show you on the side. Those key value pairs may take days to compute. So those machine learning algorithms may take days to compute those values. On the other hand, someone's profile is very fast to compute. So the definition of the cost might be the time to actually compute those key value pairs. Cost could also be the value that someone pays for the performance. So someone may walk up and say, listen, I'm willing to pay $1,000 a month to have access times lower than 100 milliseconds. So suddenly the key value pair for that individual becomes expensive and gets a cost associated with it. And we want to use the memory in order to service those costly requests. Today's solutions are rather naive. They require a system administrator, an intelligent human being who is mathematically an expert, to identify groups of key value pairs based on similar size, cost, or both. Then they walk up and they take the available memory and they break it into pools. And they assign one or more groups of these key value pairs to a group. And they use LRU to manage the data that's maintained in each one of those pools. This solution raises many, many interesting challenges, and you'll find these challenges discussed in the literature. There are papers out there that try to answer questions such as, how does the system administrator group trillions of key value pairs across a dozen applications? Or how does that administrator partition memory of thousands of cache servers? How do you come up with mapping of two or more groups to one partition? So on and so forth. And then last but not least, what happens when the administrator does a poor job or the workload evolves quickly? How will the assignment evolve and how will the assignment change? Because of these challenges, I believe this resource partitioning is a terrible solution. A better solution is a sophisticated algorithm that considers both the cost and the size. I'm pretty confident that I'll put you to sleep by describing the details of the CAMP algorithm. So let me tell you at a very high level what it does. It uses the cost to size ratio groups of key value pairs to dynamically construct these groupings where one LRU queue is used per cost to size ratio. And then the CAMP's hit is a function of the number of LRU queues that are out there. So imagine having many LRU queues instead of just one queue that is being managed by that hit data structure. The main properties of this algorithm is that its implementation is as fast as LRU, so it's order 1. It considers size, cost, and recency of references, and it's very quick to adapt to evolving access patterns. And it does not require a human being. It does the management of the space dynamically all by itself. I'll refer you to the paper at the bottom if you're interested in looking at the details of the algorithm. Let me tell you about the third challenge, NVM. So NVM is non-volatile memory. It's a new form of memory that's being introduced into the market. You can buy it today. So it's a broad class of storage technology. The key characteristics is that it's byte addressable, so it supports load and store similar to DRAM. It provides a high write throughput. It's orders of magnitude faster than SSD and HDD hard disk drives, so it has no seek or rotational delay. It may exhibit a read-write asymmetry. And as the table here shows you, it starts to compete with DRAM when we look at the speed. Its latency is in the order of nanoseconds. It's all about the speed. When you look at the performance of this device for sequential writes and random writes, in these graphs, the y-axis is the size of the block that's being read, and the y-axis is the performance. Notice that the y-axis is log scale. So there's a huge difference between those curves. So it indicates that NVM, which is the top curve, is much, much, much faster than today's flash drive and the disk drive drives that are out there. When you look at the physical architecture of a computer, in addition to NVM, we have many core motherboards. So for example, here is an example CPU die with the cores that are being shown to you. There are 4 cores right there. The caches, there's an L1 cache for each one of those cores. So imagine the L1 cache that's shown there should be duplicated everywhere. There's a larger L2 cache, there's a shared L3 cache, and then there is your memory controller. So this is your CPU die. And this CPU die, you can logically think of it as having the cores with the caches. And at the very bottom, you have your main memory, your RAM or your DRAM. Now imagine replacing that DRAM with NVM. Now your memory maintains the data in the presence of power failures. Before, every time there was a power failure, the content of the memory and the caches would disappear. With the NVM, it's equally as fast, but every time there is a power failure, the data inside of the NVM remains intact. It doesn't disappear anymore. Whereas the content of the caches on the top disappears. You can even imagine scenarios where you have hybrids, where you have RAM and NVM side by side being available to those cores for processing. This architecture raises a number of interesting questions. Believe it or not, forgetting in the presence of power failure is a great idea. It's good to have amnesia and forget everything every time there's a power failure. When there is persistence with NVM, you could have torn writes. So it's the case that the core might be busy processing something and writing to the NVM, and then there's a power failure. So it writes a record only partially, and by doing so it will corrupt the data that is inside of the NVM. The other challenge that is out there is out-of-order execution of instructions by a core. As you know, the CPU cores rearrange the instructions in order to execute them as fast as possible. By rearranging them, they may compromise the consistency of the data that is stored inside of the database. The solutions to these challenges are intricate, they are very detailed. I don't want to put you to sleep. All I'm going to tell you is that it's very interesting. A lot of work has been done. Look it up. It's pretty cool stuff that has been completed. Let me change tracks and go to the opportunities. So far I told you about 3 challenges, 3 solutions in the context of the cache augmented data stores. The key opportunity out there is that today's cache augmented data stores are very difficult to use. If you write a program using this architecture, you'll find that life is pretty miserable. The reason why is because the application programmer is responsible for maintaining the content of the cache and the content of the data store in sync with one another. That developer is responsible for using the IQ leases. And even though they look simple, actually using them, developing software with them, requires someone to understand those leases, start to write the software, debug that software, test that software, maintain that software, and every time there is a change, they must go through that cycle over and over and over. And there is still stale data that must be maintained between the cache and the persistent store. We believe that the future cache augmented data stores are going to become a middleware, where that middleware is going to hide the concept of the cache manager from the application developer. The idea is very simple. All the IQ framework and all the details are pushed into the cache augmented DBMS that is shown in the middle. The application developer is no longer aware of a cache manager or a data store. They use SQL to implement their application. It's the responsibility of that CA-DBMS to maintain the cache and the data store consistent with one another. The key features of this architecture is that it will also have to do continuous monitoring in order to adjust to the work We should also be able to adjust the system size accordingly. We should be able to use additional cache managers as necessary. For load balancing, it's very important for the switches, the network switches, to become an integral component of the caching layer. So more and more, the idea is to push the cache, part of the cache, inside of the network switch. And by doing so, the performance is not only improved, it's the case that the load is also better balanced across the individual cache servers that are out there. More longer term, it's the case that future computers are going to become biological. We're going to have RNA, DNA as our future disk drives and flash drives. And that's where the data is going to be stored. And the computation is going to be more of a chemical reaction that happens. Today, people can solve the traveling salesperson problem using a chemical reaction and a collection of strands that represent the cities that the salesman must visit. So, assuming these future architectures, the question is, where exactly are the caches and what role do they have to play? Let me stop there and answer any questions that you may have. So, for example, memcache, think of it as a giant hash table that's sitting in memory. And it's a separate server, separate process altogether, independent of the database management system like MySQL. So just two different processes. Imagine them as different processes. And it's the case that the memcache process is hosted on a different server perhaps. And there could be hundreds of servers for that caching layer. So it's for free. You can download memcache for free today, and it's available. It has a wallet client, and the wallet client is like your JDBC driver, and you use it to communicate with the cache server. That is that option.
این آخری که الان گفتیم یعنی تو سویچ رو کشش بذاریم یعنی مثلا مال SDN ایناست یا مثلا تو همین معمولی ها مثلا استفاده میکنیم.
Excellent question. That's a very good question. So it's independent of the SDN. It's actually using the memory of the switch as a key value store. And the programming of these switches is not trivial. It's not as though you have a pointer that you can manipulate. You must, when we talk about a key value store in a switch, you must deal with registers, and the programming is very, very cumbersome. It's not your traditional programming language that is done.
راجع به استفاده از NVMe ها به جای رم صحبت کردیم. سولوشن چالنجی پیدا کنیم. کامپیر پرایسش یعنی از نظر هزینه‌ای که متقبل میشن شرکت‌های
So the price is very high today. It's very expensive. It's not economical as we speak, but it's expected that the price is going to come down. Organizations like Amazon, for example, are willing to pay the price because otherwise they cannot keep up with the Black Fridays and the demand that is out there.
So you just mentioned storing on DNA for RNA sequences.
Yes.
So what is the status right now? I think I saw one study earlier this year that really happened.
it's definitely emerging. It's happening. So there are scientists, for example, I think if you look at the science issue of May, if I'm not mistaken, of this year, there were a group of scientists who took the Library of Congress and they digitized everything on the DNA. And the whole library has been captured. So it's moving fast. And I would say within the next 10 to 20 years, it'll be here.
How much is the storage of DNA or many DNAs, and how we can put Facebook on DNA, and how many DNAs?
Yeah, so every strand can store terabyte, in the order of terabytes of storage. So if you could say, I don't know, 100 strands, you've got 100 terabytes right there. So storage is not an issue. The most important part is the chemical reaction required to process the workload of Facebook. That's the main challenge.
And the chemical issues are done here?
No, it's in the process. So people are focused on storing things today, but the true challenge is really that chemical reaction, what it would look like, and how it would process billions of requests per second.
My second question is, you're talking about changing the elite and inserting keys, and how it's done, and how can we change the places of these, and how is the performance, and how is the cost for changing the delete and the insert place?
So you're talking about the different right policies,
yes.
The right true policy. So the right true policy that I described increases the cost of the software. You need a software developer to actually write the software. Let me see if I can bring it up. Yeah, so when you look at the right true, there are two forms of it. There is one where you refresh the key value pair, and notice that the software developer must do a read, modify, write in order to update the key value pair. Alternatively, it may do an incremental update. So let me give you an example of each. In Alice's example, right? So when Alice is deleted by the system administrator, the number of her friends and the number of people who have her as friends, their number of friends should be decremented by 1. Decrement is an example of the second one. When Alice changes her mood to be happy, it's an example of the top one. The application must read the key value pair corresponding to her, modify her mood to be happy, and write it back. So all of that is software. Some software developer must program all that. So the software development cycle is expensive, but the advantage, so that's a disadvantage. The advantage is that the system becomes much, much faster because it no longer will observe a miss in the cache because there was an update. Now you have the refresh data in the cache. So the system is far faster. It's also more power efficient because query processing requires power to do the processing. And by updating the key value pairs, that processing can be avoided.
Excuse me. Talking about the memories, one of the key features that the DRAM has is the advantage of the random access. And talking about the biological opportunities of memories, is that really, I think there should be a problem of accessing a random access on a chemical way on a DNA strand.
Yeah, you're raising a very interesting question. So let me tell you a bit more. Something that we have with computers is junk data. So when you look at our today's algorithms, the algorithm uses variables to compute things. If you think about my example with LRU, Notice the variables that are out there. I have a mean variable. I have a victim variable. All of that is junk. It's variables that are being used to implement algorithms. Nature is truly beautiful. It doesn't generate junk. It just does it. It just computes it. And it's pretty amazing. So when you look at a chemical reaction that happens in nature, where is the junk in it? Where are the variables? So the answer to your question is I don't know, but I think there needs to be an ultimate shift in computing. There is no longer junk data to be produced. It's going to be very efficient in the form of that chemical reaction.
So are we anticipating a kind of new field of algorithmics just for that new type of data structure?
You said they just look up instead of computing any qubits that they user keys, they just store them in the cache server, right? But how do they know how much memory is required for all these pre-computed qubits?
Excellent question, and that's where the opportunity is. So what you just asked is a future opportunity, and that's what the cache augmented database management system must answer. And it must do so by monitoring itself. It must monitor the workload, it must monitor how the caches are behaving, and it must autonomously adjust the size of the caches. So as the workload changes, it should be able to double the memory of the cache sizes. Today's cache managers are very brittle. When you start them up as a process, you must tell them how much memory they have. It's very difficult. When you start a cache manager, how do you know? Should it be 10 gigabyte? Should it be 100 gigabyte? We wouldn't know. And that's where the opportunity is for the future.
So they have to delete some of the pre-computed data at the time.
I think a better way of doing it is to have a system that monitors itself, that sees what the workload looks like, and then adjusts the memory size dynamically using sophisticated algorithms.
توی سال تقریبی داره که شما گفتید همه واسه RDBMS ها بود. در صورتی که ما تو NoSQL هم ایده کشف داریم و همین چالش هم هستش. ولی ما تو NoSQL کانسیستنسی رو تا یه حدودی مثلا معروف بشه پذیرفتیم. آیا این چالش اونجا هم هستش؟ این چالش اونجا هست؟
Yes, I focused on relational databases, but these caches also apply to NoSQL data stores like MongoDB. So if you look at the papers we've written, we show that the caches also boost the performance of MongoDB. The key observation is that even with NoSQL, when you issue a query, it must do processing. With MongoDB, for example, it must access its index structure in order to process the query. Whereas by storing the result in a key value store, we can just look it up very efficiently. So it boosts even the performance of the NoSQL data stores. Some 10 years ago, it was the case that most people had accepted the concept of weak consistency. It has changed. Even Google and Facebook say it's no longer acceptable. The reason it's no longer acceptable is because it's very difficult to write software with weak consistency. When you write software, if the data is corrupted, how do you know if it's a bug in your software or a bug in the data? That's where it becomes very challenging. So the programmer's life had become miserable at these organizations. And they've switched, they are changing because it's very difficult to develop software using weak consistency techniques. So they are more and more they are emphasizing strong consistency, even in the NoSQL camp that is out there. I still have a problem for you guys too, at the very end. So I'll get to it.
سلام، خیلی ممنون جلوی خوبتون. شما راجع به حافظه تو DNA ها صحبت کردید. خواستم بپرسم که آیا پروژه مثلا راجع به حافظه انسان اجرا میشه، این مثلا ورکینگ مموری انسان مثلا چطور کار میکنه و مثلا تو مدل‌های دیگر بهش استفاده بکنه.
Yes, there are many projects in the context of the Human Brain Project. So if you Google Human Brain Project, it dates back to 1995, when NIH, National Institute of Health in the United States, started to evaluate the human brain and how it functions. And even under the Obama administration, more and more emphasis was placed on the human brain and its processing capability. Because it's just amazing. What the human brain can do is tremendous. And yes, the short answer is there's a lot of activities in that area. Yes, they are able to grow neurons that communicate with silicon. So the computer and the neuron can exchange information. These are hybrid systems. So similar to the chemical reaction I was talking about, somehow connected to silicon, imagine neurons being grown and communicating with the silicon. Okay. So let me ask you a question. So my turn. All right, here's a question for you. So here's a challenge. Look, random generation of M requests, M concurrent requests. So imagine Facebook when there are thousands of users issuing requests at the same time, random. With N servers doesn't mean a uniform distribution of requests across servers. And I'll show you what I mean by that in a second. Here's an example from the Google file system. So Google file system shows that as they increase the number of concurrent clients accessing the servers in their data center, based on their network bandwidth, that's the rate at which they should process the request, the solid line. It's really the case that the aggregate read rate is lower. It's not as high as it should be. And the reason for that is because the requests get unevenly distributed across those servers. Here's an example. So imagine I have 3 servers, and they're shown at the very top. And I have 3 requests. So 3 users come along, and each one generates a request. There are some 27 possible permutations of how those requests get mapped to the servers. So you could have a scenario where request 1 goes to server 1, request 2 goes to 2, request 3 goes to 3. Or you could have 1, 3, 2. Or 2, 1, 3. You could enumerate them. You could also have scenarios where request 1 and 3 go to server 1, and then request 2 goes to server 2. Or you could have even more scenarios at the very bottom. I have 3 requests go to server 3, and the other servers don't receive any requests. Notice that these requests are generated randomly, but random doesn't mean uniform. Only 6 of those scenarios are uniform distribution of requests. So only the first 6 have 1 request per server. The others are truly undesirable. They have more requests than they should per server. And this is why at Google the aggregate read rate is lower. It's really the case that these requests are colliding with one another. And that's why the rate is lower. So here's the question. Given arbitrary values of m and n, where m is the number of concurrent requests and n is the number of servers, what are the different combinations of mapping requests to nodes and their probability? Can you compute that? If it's too hard, then can you compute the probability of a uniform distribution of requests across the nodes? What's the probability of having n over n across those nodes? And when you come up with a solution, if you design an algorithm that you implement in software, what maximum values of n and n would your solution support? So if it works for, say, 3 nodes and 10 requests, that's great. But remember, Facebook and Google have data centers with hundreds and thousands of servers in them. So would your solution work with such large values of n? They process billions of requests per second. Would it work with value of n in the order of billions? Can you do the computation? Email me your solution. I would love to hear from you. If you develop the software, give me your GitHub link and I'll look it up. I'll be excited to see what you have. Thanks. کامپیوتر SSC در حال برگزاری است. بازم عذر می‌خوام هم بابت این ایرادات پیش آمده، عدم هماهنگی‌ها و تأخیر ابتدای جلسه‌مون. خب در حاشیه سمینار شرکت پوشه با همکاری SSC مسابقه داده‌کاوی برگزار می‌کنه به نام دکا. این مسابقه در حوزه ماشین لرنینگ هست. از اول دی ماه آغاز شده و تا پایان بهمن ادامه داره. موضوع مسابقه پیشبینی احتمال کلیک کردن روی پوش نوتیفیکیشن ها هستند. داده مسابقه 100 میلیون اینتراکشن واقعی از 4 میلیون کاربر است و جایزه مسابقه هم در مجموع 20 میلیون تومان. توضیح فنی مسابقه فردا ساعت 11:30 تا 12 در تالار 5 ارائه میشه. اگر هم سوالی داشتید میتونید بچه‌های مسابقه دکا رو با لباس سبز توی تالارها پیدا کنید. و نکته آخر همین که در پکی که در اختیارتون قرار گرفته یک سری برگه پرسش و پاسخ هست که توضیحاتمون رو تو کانالمون ببینید. حتما نظرسنجی هایی برای هر ارائه توی باتمون در نظر گرفتیم که به ما و ارائه دهنده ها تو بهبود کارشون کمک میکنه. خب شما رو دعوت میکنم که کمی سریعتر به سمت تالارها حرکت کنید. سخنرانی بعدی رأس ساعت 12 برگزار میشه. متشکرم.